Welcome to the fifth lecture of week 2. We will continue our discussion on the elasticity based approach. So, in the last class we found out the E1, and for that the loading condition was that these concentric cylinders are loaded along direction 1. Now, here also the loading condition remains same. So, our interest is in the quantity nu 1 2, which can be defined as minus epsilon r divided by epsilon 1. Now, our response is as axisymmetric. So, we can say that epsilon 2, that means transverse strain along the direction 2 is same as epsilon r. So, that is why it is minus epsilon r by epsilon 1. Now, epsilon r at, we have already done the solution. So, from this we already found out u and epsilon 1. So, from that we can find out epsilon r at r equal to b, that means at the surface of the cylinder, outer cylinder is u m b by b. So, u m evaluated at b by b, and so that is nothing but a m plus b m by b square divided by epsilon 1. Now, with that we can find out that if you do divide by the epsilon 1, then this quantity is just nu 1 2. So, epsilon r is a m plus b m by b square, and if I divide that by epsilon 1, then it is nu 1 2. So, we already know a m, b m and epsilon 1, and that means we have seen how to find those out. So, with that nu 1 2 can be evaluated as nu 1 2 is equal to V f into nu 1 2 f plus V m into nu m plus a term which consists of V f multiplied by V m multiplied by nu 1 2 minus nu m, and then this entire thing multiplied by 2 into E 1 f nu m square plus nu m multiplied by E f minus E 1 f. So, minus E 1 f plus E m minus E m into nu 1 2 f plus 2 into E m into nu 1 2 f square, and then this entire thing is divided by that same h which we obtained in the last class as a part of the expression for E 1. Now, with that we will move on to the in plane shear modulus. So, for finding out the in plane shear modulus, again we take these concentric circles, two concentric circles. We have fiber at the center and matrix at the outside. The diameter of the fiber part is 2a and the diameter of the matrix part, I mean the entire thing is 2b, and then we load it with a shear strain nu 1 to 0. So, we assume that it is subjected to a shear strain nu 1 to 0. So, we write that composite cylinder subjected to a shear strain, and that shear strain is gamma 1 to 0, it is not nu. Nu is generally used for denoting Poisson's ratio, and for shear strain it is gamma. Gamma 1 to 0. Now, we make some assumptions for our variables u 1, u 2 and u 3. u 1 is displacement along 1, u 2 is displacement along 2 and u 3 is displacement along 3. So, for u 1 the assumption that we make is minus gamma 1 2 0 by 2 into x 2 plus a function f of x 2 and x 3. Now, the rationale for getting this function can be found out by the papers that we referred. Here we are just taking as it is, and then we have u 2 is equal to gamma 1 to 0 by 2 into x 1, and then another assumption is u 3 is equal to 0. So, with that we can write epsilon 1 1. Now, normal strain along direction 1 is related to the displacement along direction 1 as this, and if we evaluate with these assumptions, then the quantity becomes 0. Similarly, other normal components are also 0. Now, we evaluate the shear terms. So, we have gamma 2 3, which can be written as del u 2 3 by del x 3 plus del u 2 by del x 3 plus del u 3 by del x 2, and that quantity is can be written as zero. Similarly, we can write del 1 2, that is gamma 1 2, that is del u 1 by del x 2 plus del u 2 by del x 1, and if we evaluate that, this becomes del f by del x 2. Similarly, the other shear, which is gamma 1 3, that we can write as del u 1 by del x 3 plus del u 3 by del x 1, and again with that approximation we can write this as del f by del x 3. Now, finally, we can put all these approximations in the equilibrium equation along direction 1. So, equilibrium equation along direction 1 can be written as del sigma 1 by del x 1 plus del tau 1 2 by del x 2 plus del tau 1 3 by del x 3 is equal to 0. So, taus are the shear components. Generally, we use sigma for denoting the normal stress components and taus for the shear components. So, tau 1 2 shear stress is G 1 2 multiplied by gamma 1 2 with G 1 2 being the shear modulus. Similarly, tau 1 3 is G 1 3 into gamma 1 3, and also we here assume that G 1 2 and G 1 3 are same. So, with that we can write this as G into gamma 1 2 and G into gamma 1 3. So, if we put this approximation in this equation, then finally, the equation that you get is del 2 f by del x 2 plus del 2 f by del x 3 2 is equal to 0. Now, here we can make an assumption for x 2 as x 2 is equal to r into cos theta, with r being the radial direction and theta denoting the circumferential direction. Similarly, x 3 is equal to r sin theta, and that gives us that x square is equal to r square is equal to x 2 square plus x 3 square, and theta is equal to tan inverse x 3 by x 2. So, these two are just consequence of these two assumptions. So, if we put these considerations in this equation, then this equation turns out to be del 2 f by del r 2 plus 1 by r into del f by del r plus 1 by r square into del f by del 2 f by del theta 2. Now, for this kind of problems we have seen that we can assume the solution as f as a function of r and theta as a r plus b by r into cosine theta. Now, we can put these approximations in the equation and then we can have some conditions applied like we did before. So, here the conditions is that U1 is continuous at the junction between the fiber and matrix. So, U1 f is equal to U1 m when r is equal to 1, and that gives us A1 into A plus B1 by A is equal to A2A plus B2 by A. Second condition is that U1 f at r is equal to 0 is finite, and that tells me that B1 is equal to 0. In fact, we can make this, you could have made this assumption before itself, and instead of assuming U1 within fiber as A1A plus B1A, we could have assumed just it as A1A. Then the third one is the shear stress is continuous. So, shear stress tau R1 Rf at r is equal to A is equal to tau 1 Rm at r is equal to A. They are continuous, and the third, so this one says that Gf multiplied by A1 minus B1 by A square is equal to Gm multiplied by A2 minus B2 by A square. And again, if we assume that G has different shear modulus in different plane because of being anisotropic, so accordingly we have to have G1 R here. And then we have the fourth one, which says that U1 m at r is equal to B, and that can be written in terms of the applied shear strain gamma 1 to 0 as this, and that evaluated at r is equal to 0. Now, with that we get A2B plus B2 by B is equal to gamma 1 to 0 into B. So, if we put all these conditions, then finally the shear modulus comes as G12 is equal to Gm multiplied by a term where we have in the numerator Gf into 1 plus Vf plus Gm into 1 minus Vf, that means Gm into Vm, and again to be precise, as mentioned before, we can write this as G12 because our fiber can be anisotropic, and then we have G12 f multiplied by 1 minus Vf plus Gm into 1 plus Vf. So, this becomes our expression for the shear modulus evaluated using the theory of elasticity based approach. Now, to find out the transverse modulus, we cannot directly apply this two cylindrical model. Now, by the way, in the theory of elasticity based model, we have always concentric cylinders. So, this is called a concentric cylinder based approach also. In the previous cases, we had always two cylinders, inner one with fiber and the outer one with the matrix properties, but that only gives us bounds for the transverse modulus. So, using this approach, if you want to find out the exact value of the transverse modulus, then we assume three cylinders, the inner one being fiber, the intermediate one being matrix, and the outermost one is the has the homogenized property. That means, whatever we are trying to find out, we assume that the outer one always already have that. So, again these are the different views of the same cylinder. Now, we are not going to the exact derivation of this using this model, because this is quite involved and that is not in the scope of this course. So, we are directly going to look at the conclusion of what we get from this model. So, as per this model, this becomes the expression for E2 elastic modulus along direction 2, and we can see that this E2 is a function of now nu 23 and G 23. Now, nu 23, this Poisson's ratio can be written as this, where m again can be written as this. So, ultimately in this expression we are introducing another unknown, which is k star, and m is also a function of this k star, and k star denotes k denotes here bulk modulus. So, k denotes here bulk modulus. So, if I have K m, that is bulk modulus of matrix, and if we have K f, that is bulk modulus of fiber, and we need other quantities like matrix shear modulus and so on. So, with that we can find out K star, and then so here we have written the expression for K f, but again this assumes isotropic fiber behavior. Based on the anisotropy, this equation can change. Now, for finding out the other unknown G 23, we have to solve this nonlinear equation. Now, in this nonlinear equation there are three constants A, B and C, these are all known constants. So, A is this, B is this, and C has this big expression, and again we have introduced some another new term here, that is etas, eta f and eta m, and those eta f and eta m in terms of the Poisson's ratios as this. So, with this E2 can be evaluated, and this involves a 3 cylinder model as opposed to the 2 cylinder model. So, this brings us to the end of this elasticity based approach. Now, we will briefly look into the other approaches. So, there is something called self consistent method. In the self consistent approach, we assume that there is a fiber and that is embedded in a unbounded homogeneous medium, and we know the property of that we do not know the property of that medium, because we assume that the fiber that is embedded in that unbounded homogeneous medium, that medium itself has the property of the composite, which is our desired property, which is something that we want to find out. And this entire assembly macroscopically behaves as that of composite, and we assume that the medium is subjected to uniform load at infinity, and that results in uniform strain in the fiber. And then we evaluate the elastic constants based on the strain field. So, here the main difficulty is that we are assuming that the fiber is bounded by something, and interestingly that bounding medium itself has the unknown property which we are trying to find out. So, this leads to some kind of iterative approach. For more details, these papers can be referred to. We are not going to the detailed mathematical description of this model. Now, there is another very famous approach that is called the Muri Tanaka model, and this assumes that the fiber is embedded in an infinite matrix medium. So, here also the fiber is embedded, but instead of being embedded by that unknown homogenized medium, it is embedded by the matrix medium. So, here the good thing is that we already know the property of the matrix, and then SLB's inclusion theory, which can be found in this paper, is used to relate the strain in the inclusion to the far field strain, I mean the strain under which it is subjected to, and then we incorporate the inclusion interaction by considering matrix as the reference material and adjusting the far field strain experienced by each inclusion. Now, this method, the details of this method can be found out in these papers. This is the paper by Muri where this was described, Muri and Tanaka. Now, this method works quite well when the fiber volume fraction is relatively less. In that case, the self consistent method can work, but the problem here there is that is more complicated because of having the bounding material itself being unknown. Then there is another approach which is gaining quite popularity, rapid popularity nowadays, and that is the numerical approach. In the numerical approach, we do the solution by using numerical techniques like finite element method. So far in all the approaches, whatever what we have done is we assume an RV and we assume that it has either given stress or strain, and then we try to analyze what is happening inside, and then from that solution we try to find out the equivalent elastic modulus and other properties. But those solutions were mostly analytic or semi analytic. So, that is why we could not relax many of the assumptions. But nowadays the computational power is increasing rapidly. So, we can afford to do the numerical solutions here, and with the numerical solution the benefit is that we can afford to relax many of the assumptions. So, when we do numerical solutions instead of these approximate analytical solutions, we can handle more complex microstructures like woven, braided, random fibers and so on. Similarly, so far we have assumed that the fiber and matrix are linear and isolinear, but in reality they can exhibit nonlinear behavior, they can be viscoelastic, they exhibit plastic behavior also. Also, there was no way for us to or limited possibility for us to include damage or voids in the medium, but here we can do that, or any other imperfection can also be accounted for. So, that is why the numerical approach has been gaining lot of popularity nowadays. So, there has been a good number of research papers published in last 2 decades. So, interested learners can refer to those. So, composite micromechanics can itself be one subject to teach, but here because of limited scope we just looked at the mechanics of material based approach in more details and with some details on the elasticity based approach, and we just touched the other approach very briefly. And then in the following weeks we will use these conclusions, we will use the homogenized properties to do the actual analysis of the composites. So, with this I would like to conclude this lecture here. In the next lecture we will solve some numerical problems based on the equations that we derived so far. Thank you.